Hello and welcome to a demonstration of the tangent approximation app. My name is Adam Hausnecht. To run the app, I'm going to use a terminal window. This is the yellow window you can see here. Now what we have to do is change to the directory that contains the app, which is over here on the desktop. To do that, I'm going to use the cd or change directory command. I'm also using the tab key to avoid having to type so much. Okay, so now we're at the tangent approximation test directory, and now to actually see the contents of that directory, I need to use the ls command. Okay, so here's the contents of that directory displayed now, and you can see the most important file is the actual application program, and also here is a completed library file that is necessary for the program to run, and here's a version that students will have to complete in order to have a running program. Automatically, each time you run the program, this subdirectory is created by Python itself. Now over here are example files. These example files illustrate how to use your own functions, that is to create your own functions using Python to use with the application program. Currently, the test function built into the program is a quadratic. Okay, now to actually launch the program, I'm going to use the Python command, Python, and then I have to use the full name of the application program, including the suffix. So I'm just cutting and pasting it in. All right, so now here's the full name, and I just press the return key. Okay, so now we have a running app. Make the window a little bit bigger. Okay, so over here, you can notice that the default quadratic has been plotted. The default quadratic is 10 minus x squared quantity divided by 2. And on the left over here is the user interface. Many of you can undoubtedly figure out what these edit fields and buttons do, but I'm nevertheless going to go through them somewhat systematically. To actually start using the program, you need to enter a value of x0. You can do that by either clicking in this edit field and typing, or by clicking somewhere in the graph window. As I move the cursor over the graph window, if you look down in this gray area, you'll see the coordinates of the cursor being displayed. I'm going to click near a place on the graph where the value of x is 2. See if I can get a little bit, okay, right about there. All right, well, I almost got 2 exactly on. So here's 2.0095, which of course rounds to 2. And if you substitute 2 into this equation, you get 3. So over here, what we have is a secant line, which is supposed to approximate the true tangent line at this point. To see the true tangent line at this point, I'm going to check this box. And now also the slope of the true tangent line is displayed here, which is the same as the derivative of f at x0. And I forgot to say, this point right here is p0. That's the black dot shown on the curve. That's where we're trying to find the tangent. Okay, so now currently the left secant is not a very good approximation to the true tangent, and so the slope of the left secant, which is 1.5, is not a very good approximation to the slope of the tangent, which is minus 2. So to improve the situation, I'm going to use the forward arrow. So if I click a few times, maybe a few more times, maybe one more. Okay, so now what we can see at that the left secant now is has a slope of minus 1.97, which is reasonably close to minus 2. We know that this is a true secant because h is minus 0.07, which means this little blue dot is to the left of P0, which is the little black dot, or bigger black dot. Also, these two lines look almost identical at this point. So now we also can back up. If you click on the backward arrow, you can back up to a previous situation, and of course you can move forward again. Okay, so now I'm going to switch to a different method. Let's use the left-right secant method, which actually creates two secants, a left and a right secant, but I want to reuse the point I previously entered, so I'm going to click in this edit field and press the return key. Okay, so now we can see the two secants. We have a left blue secant and a right pink secant, and now both of them are actually pretty bad approximations to the true tangent, and so not surprisingly their slopes of 1.5 and minus 3.5 are not good approximations for the true slope of the tangent, which we know is minus 2. Again, we can improve this by moving the blue point and pink point closer to the black point by using the forward button, which just generates the next secant that's closer. I'll keep on doing this a couple more times. Maybe one more time. Maybe one more time. All right. So at this point, we have an approximate slope of minus 1.99. That's the average slope. That's a better approximation than either the left slope, which is minus 1.98, or the right slope, which is minus 2.01. So the left slope actually is, you might say, a little bit too positive, and the right slope is a little bit too negative. In any event, if we want to go back to a previous approximation, we can just use the back arrow. Also, if for some reason you wanted to save a copy of the screen showing the configuration of the secants and the tangent line and these values up here, you can just click on this little floppy disk icon. This opens up a window where you can navigate to where you want to save the figure. I'm just going to save it on the desktop. Let's see. Desktop. Let's see. Okay, so here it is down on the desktop. Now, to see that it actually worked, I'm just going to open it up. And now you can see it is a copy of whatever you see on the screen right now. Okay, now you might want to do that because as part of a homework assignment, or because you want to save a record of what you were doing. Okay, so now I want to show you one more feature. If you move forward, if you really want to go all the way back to the beginning of the sequence of secants that you're using to approximate this tangent line, you can click in this restart button, and now you're back to the initial configuration of the two secant lines. And of course, you could move forward again if you wanted to. Okay, so now I'm going to switch to a different method, the central difference method. And now I'm going to use the repoint again, the initial point I selected by clicking in the Exeruet field and pressing the return key. So here we are. Now, what you can see here is the central difference secant. It passes through 2 points, this pink point and this blue point up here. What's interesting and somewhat surprising is that these two lines are actually parallel. That is, the green secant line is actually parallel to the accurate representation of the tangent line. And you know these two are parallel because the slope of the central secant is -2, which matches the slope of the true tangent line. And how is that happening? Well, just to see that it's not an accident, let's just move closer. Okay, so I've moved closer, and now the secant line is still parallel. The slope is still -2. Now you might think this is some kind of luck by the point we selected, but let's try a different point. How about if we try 0? So I'm using the edit field to enter in the value of x0 because I want to enter it in exactly, so I need to press the return key. Okay, so now we have the true tangent line, or an accurate representation of the true tangent line at the top of this curve, and clearly it's horizontal, and that shouldn't be a big surprise because at x equals 0, this is a local maximum, and it's just a property that at local maximums and local minimums, if you have a reasonable function, the derivative is going to be 0. Now, down here you can see the central secant line, and it too is horizontal. That is to say, its slope is also 0. That's why you have a 0 here. Now, currently, it's as far as it can be from the true tangent line. So what we can do is we can move it closer, and of course, it stays. So actually what's going on here is it turns out that the central difference secant line, this method always gives you the exact result, that is the exact value of the derivative for quadratic functions, and this happens to be a quadratic function. It also gives you the exact value for linear functions. So you can actually try to prove that yourself. It's not very difficult. Okay, so now finally what I want to do is show you how to reset the app. You can do that by clicking on this reset button. Now this restores the app to more or less its initial configuration, that is when you first start the app, except for the method of you're using to approximate the tangent, the true tangent. And finally, to quit the app, all you need to do is either press click on this quit button down here, or at least on a Mac you can click in this a little red box up here, red button up at the top. So I'm just going to click in the quit button. Okay, so when you quit, a message saying that the app ran successfully and is displayed. So tangent approximation app ending, bye-bye. Okay, so that's it for the demo. Thanks very much for your attention.